Welcome to this explainer. I am absolutely thrilled you're here today because, well, we're going to completely change how you look at something you've probably seen 1,000 times. When most of us look at a swimming pool, we just see a refreshing body of water, right? Just a simple structure to cool off in. But today, we're reframing that everyday pool as a highly calibrated, totally invisible machine. Beneath that calm, shimmering surface is this fascinating, complex world of mechanics, geometry, and heavy-duty math. Okay, let's dive into this. Pun totally intended. We need to shatter the illusion right away. A swimming pool is absolutely not just a hole in the ground lined with concrete and filled up with a garden hose. No way. What we're actually looking at is a marvel of meticulous engineering. It's a rigorous planning process that has to be entirely mapped out before a single shovel of dirt is ever excavated. It's essentially an intricate dance of hydraulics and structural design. To really understand how this invisible machine works, here is our roadmap for the explainer. 1. The blueprint. 2. Anatomy and geometry. 3. The math of water. 4. Occupancy limits. And 5. Functional zones.
All right, let's kick things off with Section 1, the blueprint.
Proper planning is the ultimate foundation here. It really isn't just about figuring out where the pool looks best in a backyard. I absolutely love this quote. Every successful swimming pool begins long before excavation starts. It perfectly captures the fact that the real magic, the heavy lifting, happens right on the drawing board. You have to integrate complex systems well in advance to ensure structural integrity and honestly just so everything operates seamlessly later on.
Just look at this list of systems that engineers have to coordinate. It's wild. We've got hydraulic systems for water flow, structural design to hold back literally thousands of pounds of pressure, filtration equipment, sprawling plumbing layouts, electrical services, which, have to run safely near water, and of course, chemical water treatment. Coordinating all these invisible systems is absolutely non-negotiable. It's what ensures safe operation, regulatory compliance, and comfortable swimming, while also optimizing your construction costs down the line. Moving right along to Section 2, Anatomy and Geometry. So when we look at the shape of a pool, we tend to think of it as just an aesthetic choice, right? But in reality, the geometry dictates exactly how the water behaves. We're going to look at the 4 most common pool shapes engineers work with: rectangle, freeform, circular, and L-shaped. These aren't just design preferences. Each one comes with very specific hydraulic pros and cons that engineers have to carefully navigate. Check out this stark contrast between the classic rectangle and the organic free-form pool. Rectangles, they're an engineer's best friend. They provide incredibly simple hydraulic design and super uniform water circulation. Free-form pools, on the other hand, they look beautifully natural and offer awesome architectural flexibility, but they come with a massive engineering trade-off. All those sweeping curves demand incredibly careful hydraulic balancing to make sure the water actually flows properly into every single nook and cranny. Then we have circular versus L-shaped pools. Circular pools create wonderful, symmetrical circulation patterns, but honestly, they can be a real headache to integrate with surrounding deck layouts. L-shaped pools are fantastic for functional zoning, like keeping a swimming lane totally separate from a chill-out area. But there's a catch. That sharp inner corner creates what engineers call dead water areas. So the engineer has to essentially outsmart that geometry with strategic plumbing to keep the machine running cleanly. And this brilliantly illustrates how usage dictates depth. Look at that massive jump. We start with a 1.2 meter shallow area for kids, maxing out at 1.8 meters for standard recreational swimming. But the second you introduce diving, the requirements just skyrocket. Depending on the platform height, diving pools require a huge, sudden jump in depth, usually exceeding 3.6 meters to guarantee absolute safety. Which brings us to Section 3, the math of water. Once the geometry is locked in, we transition into the hidden mathematics. Calculating the total volume of water is the master key here. Why do engineers obsess over exact volume calculations? Because volume determines literally everything else. It dictates your filtration flow rates, pump selection, exact chemical dosing, heating capacity, and turnover time, which is how fast all the water passes through the filter. Without precise math, the pool just cannot maintain safe or comfortable conditions, period.
So how exactly do they do it? It's kind of like an aquatic trade secret. For rectangular pools, it's straightforward: length times width times depth. For circular pools, you use the classic area formula of pi times radius squared, multiplied by the depth. And for pools with varying depths, which, let's face it, is most of them, engineers first have to calculate the average depth before they can even figure out the total volume.
But what about those tricky, curvy, free-form pools we talked about earlier? Engineers break this complex beast down into 3 bite-sized steps. Step 1, calculate the average depth. Step 2, visually divide that wild free-form shape into smaller, manageable geometric sections like overlapping circles and rectangles. And step 3, calculate the volume of those individual sections and combine them for the grand total. It's a pretty brilliant way to tame a complex shape with simple math.
Now for Section 4, occupancy limits.
This is where we bring the human element back into the equation. A pool isn't just a static bowl of water, it's a dynamic environment. And once bodies enter the water, they actively change the mathematical requirements of the whole machine. Let's talk occupancy capacity. This is the maximum number of swimmers a pool can safely accommodate. And listen, these limits aren't just arbitrary rules made up by a lifeguard to ruin your fun. They are strict calculations directly tied to safety and sanitation, sizing the water treatment capacity, chemical consumption, and even emergency systems.
So the crucial point here is the number 1. Seriously, even just one single swimmer entering the pool immediately throws a wrench into the system. One human introduces variables like sunscreen, sweat, and movement, and that instantly starts consuming chemicals and demanding active filtration.
It's a very direct cause and effect relationship. As the number of swimmers increases, the stress on the pool's hidden machinery increases right along with it. To compensate, the hydraulic system has to be engineered to provide greater circulation, push higher filtration rates, and deliver incredibly efficient water treatment. Basically, the machine has to work a lot harder the more people are in there enjoying it.
Finally, let's wrap up with Section 5, functional zones.
This is the final stage of planning. Engineers map out highly specific areas to ensure maximum safety, comfort, and efficiency. Imagine you're in a helicopter looking straight down at a modern pool layout. What you're really seeing is a multi-purpose aquatic machine separated into 5 distinct slices: leisure, swimming, diving, children, and spa. Each slice has a very specific job.
Let's break those down really quickly. Leisure zones provide shallow seating just for relaxing. Swimming zones are optimized for recreational movement and laps. Diving zones give you the deep water needed for safe jumping. Children's areas maintain shallow, easily monitored depths. And spa zones incorporate heated water and hydrotherapy jets. Proper zoning isn't just about organizing the fun. It drastically improves circulation efficiency and operational safety across the board. To bring it all together, successful pool engineering is the ultimate balancing act. It combines architecture, structural design, hydraulics, mechanical systems, electrical services, and water treatment into one fully integrated design. Whether it's a backyard oasis or a massive commercial facility, this comprehensive planning reduces operating costs and ensures the whole system remains reliable for decades to come.
So I'll leave you with this thought. Next time you stand at the edge of a pool ready to dive in, are you just going to see a simple hole filled with water? Or will you see the incredibly complex, mathematically balanced, invisible machine working brilliantly right beneath the surface? Thank you so much for joining me on this explainer, and keep looking deeper into the world around you.